Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today our discussion will be on Module 7, which is the fourth of 5 segments based on rational numbers. The particular topic that we're talking about today will be called decimal fractions, and it will be the topic of both this module and the next module. On the way into work today, I picked up a newspaper, and a column, a syndicated column, is called Today's Chuckle. And today's chuckle said, the man that said that marriage was a 50-50 proposition either didn't understand women or he didn't understand fractions. Now, I don't mean this in a sexist way of any sort. What caught my eye in this little piece of humor was the phrase 50-50. 50-50 signifies equal. But if things are equal, why not say 1-1 or 7-7 or 29-29? Notice that the phrase 50-50 basically comes from the concept that led to percent. See, on a scale of 100, 50 would be halfway. See, we don't say 5-5 or 500-500, we say 50-50. On the other hand, we do use other powers of 10 in discussing certain probabilities. We'll talk about we're batting 1,000. We don't say we're batting 10 or batting 100, but we're batting 1,000 when we're doing very well. And if something has a very small chance of happening, we say there's what? 1 chance in a million. And if we're referring to certain other things, we sometimes refer to someone as being a 10. And when we say that someone is a 10, on a scale of 100, 10 wouldn't be a very impressive score. So usually when we use the term a 10, we mean based on a scale of 10. And so what I'd like to do today is to show how we try to generalize the concept of percent to carry through to all ratios involving powers of 10. So let's go over to the board and take a look at what we want to talk about today. See, I call today's lesson per powers of 10, and if that sounds like a heavy phrase, remember last module we talked about percent, and cent is what? 100, and 100 is the second power of 10. See, now we're going to talk about per 10, per 100, per 1,000, per 10,000, and let's take a look how this looks. Let's suppose you got back a test and you scored 80%. What does that mean? Percent means per 100. Per 100 means divide by 100. In fraction form, that's 80 over 100, which we read as 80 hundredths. Notice that you could have taken 80 over 100 and reduced that to 8 over 10, in which case that would have been called 8 tenths. You also could have multiplied numerator and denominator by 10, in which case the fraction would have been 800 over 1,000, and we'd have called this 800 thousandths. Notice the adjective noun bit here again. See, the adjectives are 8, 80, 800. The nouns are tenths, hundredths, thousandths. But notice that they all name the same rate. Now, why would we do something like that? Well, let me just try to show you something here. Suppose we were counting by tenths. If we were counting by tenths, we'd be in trouble if we wanted to give a score which was more than 8 but less than 9. You see, we'd have to invent mixed numbers in that particular case. If we switch from a scale of tenths to a scale of hundredths, that means parts per 100, now you see that same measurement allows us to go in between 80 and 90. See, the 8 tenths to 9 tenths expands to 80 hundredths to 90 hundredths. That gives us a scale of 10 to work with. And if we switch to thousandths, you see, we can get from 800 thousandths to 900 thousandths. We can start giving out scores like 801, 802, 803, etc. And this allows us to fine-tune, so to speak. Let me run through some fairly simple problems with you, just so you start to get a feeling for what later is going to be called decimals. First problem today says, on a scale of 0 to 10, how much is 3/8? In other words, if you're going to give a person 3 out of 8, how much would you have given that person scaled up to 10? Well, this problem is quite simple in terms of what we've already learned. On a scale of 3 out of every 8, 3/8, how much would we take out of 10? That's precisely what we mean by 3/8 of 10, multiplying through here, or if you wish, you could divide through here by 2 and get 3 4/5 over here. In any event, 3/8 of 10 is 30 over 8, which is the same as 3 3/4. And all that means is at a rate of 3 out of every 8, you're taking 3 3/4 per 10. And whenever you're talking about per 10, that means you're dividing by 10, and the noun we use for that is called tenths. Do you see the subtlety of this? When you say a number like 6,000, that means 6 times 1,000. If you wanted to divide by 1,000, see, why would you divide by 1,000? Well, if you were taking 6 per 1,000, see, per means divided by. See, so when you want to divide by 1,000, instead of saying 1,000, you say thousandths, okay? And that's basically the idea over here. So at a rate of 3 out of every 8, you're taking 3 3/4 out of every 10. And notice now that the noun that's modifying tenths is 3 3/4, which is a mixed number. So we say, okay, let's see what happens if we switch to a scale of 100. On a scale of 0 to 100, how much is the rate 3/8 equal to? In other words, at a rate of 3 out of every 8, how many would you be taking out of every 100? So what we would do is we would take 3/8 of 100. So 4 goes into 8 twice. 4 goes into 125 times. That's the same as 75 over 2. 75 over 2, divide the 2 into 75 to convert it into a mixed number. That's 37.5. So at a rate of 3 out of every 8, you're taking 37.5 out of every 100. You see 37.5 per 100, which, by the way, based on the last lecture, that's what we were calling 37.5%. See, when the power of 10 is 2. When we're talking about hundreds, we're talking about percent. And so another way of saying this is that 3/8 is the same as what? 37.5 hundredths. And do you notice how the adjective is changing? That somehow or other we're getting into a bigger number as an adjective, but we're also describing a different noun. And hopefully, eventually our mixed number, we hope, will turn into a whole number because we're much more comfortable with whole numbers than we are with mixed numbers. So we carry this problem one step further. We say on a scale of 0 to 1,000, how much is 3/8? Well, same style again. 3/8 of 1,000, 8 goes into 1,000, 125 times. 3 times 125 is 375. So at a rate of 3 out of every 8, you're taking 375 out of every 1,000. And how do we write that? 375 thousandths. Do you see the idea here? And by the way, look how you could have done this back as a common fraction problem. 8 goes into 1,000 125 times. If we multiply downstairs by 125, we also have to multiply upstairs by 125, and that would give us what? 375 over 1,000. And by the way, that's how baseball averages are computed. When a baseball player gets 3 hits and 8 times at bat, he's got 3 out of 8 hits. And when you say, what's he batting? They say 375. And what they mean is, if he were to continue at a rate of 3 hits in every 8 times at bat, which is very unlikely, but at that rate, he would get 375 hits in 1,000 times at bat. You follow the idea? Now, look what happened over here. We were very, very lucky on this problem. And the reason that we were lucky is that the prime factors of 8 happen to just be 2. See, 8 is 2 times 2 times 2. What happens to a power of 10? The only prime factors of 10 are 2 and 5. So if you had 1,000, you'd have 2 times 5 3 times. And you see what happens over here, every time I multiply a 2 by a 5, I can build a power of 10. So you see, when the denominator was 8, I could get to 1,000. But the problem is, if I have a denominator that has prime factors other than 2's or 5's, I'm going to be in a real mess whenever I talk about parts per power of 10. And let me just show you what I mean by that. Let's look at a problem similar to what we were talking about before, but now I'm going to say, on a scale of 0 to 10,000, how much is 1/3? In other words, if you're taking 1 out of every 3, how many will you take out of 10,000? Well, that's precisely the problem, 1/3 of 10,000. And that means what? 10,000 divided by 3. And this becomes like a broken record. 3 goes into 10 3 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. And I finally wind up with 3,333 and 1/3. And no matter how many zeros I tack on over here, there is no chance of getting rid of this mixed number, because notice that no matter how many zeros I tack on over here, the only prime factors of a power of 10 are going to be 2s and 5s, and I have what over here? A 3. A 3. 3 will not go a whole number of times into any power of 10. So no matter how I do it, I'm going to wind up with an answer something like this. In other words, at a rate of 1 out of every 3, I'll be taking 3,333 and 1/3 out of each 10,000. If that bothers you, notice how we tend to round off. See, what is 3,333 and 1/3? It's more than 3,333, but less than 3,334. So we'd say, okay, you're taking more than 3,333, but less than 3,334 out of each 10,000, okay? And basically we say, why quibble? Though, can you visualize in certain problems where being off by only 1 part in 1,000 could lead to an astronomical error? You see, it's not how much you're off, it's how much tolerance you're allowed. If you're measuring the difference between 2 towns and you're off by 6 feet, no one really cares. In other words, if you say it's 10 miles, the guy says you were wrong, it's 10 miles, 6 feet. We round off to the nearest foot. If you're doing brain surgery or a heart transplant and you're off by 6 feet, you got the wrong body. See, basically, 1,000th of an inch can be very significant in one measurement, but a half a mile can be insignificant in another. That's something we're going to have to get into in more detail when we get to the applications here. And all I wanted to bring out by this is to show you where Module 8 will come in. You see, for the time being, we are going to look just at rates in which the denominators are basically powers of 10, so that have factors which are either 2s or 5s, so we don't get into the problem of trying to get an exact number of hundredths or thousands or 10,000s in the case where it can't be done. And with that in mind, let's take a look and see how we handle something like this. What I call this is place value expanded. You see, when we originally had place value, you started with the ones place, then you got the tens, then you got the hundreds, okay? And how did you get from one place to the next? You kept multiplying by 10. See, you're multiplying by the powers of 10 this way. And that was when you assumed that 1 was the smallest possible denomination. But now suppose you want to talk about parts per 10, parts per 100. Let's see if we can construct this. You see, if reading from right to left we're multiplying by 10 every time, then to divide by 10 must mean if we read from left to right. Let's just check this thing out. If we divide by 10, 100 divided by 10 is 10. 10 divided by 10 is 1. By the way, dividing by 10 is the same as multiplying by 1/10, and multiplying by 1/10 is the same as taking 1/10 of. See, 1/10 of 100 is 10. 1/10 of 10 is 1. What's 1/10 of 1? 1/10 of 1 is 1/10. 1/10 of 1/10 is 1/100th, etc. You see what's going to happen? Just as the powers of 10 appeared over here, now the powers of 10 are going to occur in the denominator with the numerator being 1. That's the easiest way to remember this. But watch how it preserves place value. Notice that since we kept dividing by 10 as we went from left to right, as we go from right to left, we're going to be multiplying by 10s. And that means that just like with whole numbers, 10 of any denomination will be 1 of the next denomination. And if it makes it easier for you to visualize, think of this in terms of money. See, 1/100th of a dollar is a cent. 10 cents make 1 dime. 1 dime is 1/10 of a dollar. In fact, that's where the word dime comes from. It's a corruption of the word decimal. Now, watch what happens over here. Suppose I make a chart. Something new has happened here. In the past, when we talked about place value, the smallest denomination we had was 1. Now we can have what? Tenths, hundredths, thousands, 10,000s. So suppose I put a 7 in the thousandths place. As long as the denominations are visible, I can see that the 7 stands for thousands. In other words, 7 is an adjective, it's modifying thousands. If I take the chart away, how do I know what column the 7 is? You see, 7 is an adjective, but 7 what? 7 what? And the way we get around that is we introduce a second type of placeholder. Remember, we introduced 0 to hold the place of a denomination. Now we have to hold the place to tell us where the ones are. You see, no longer can we be certain that the digit furthest to the right is 1. So what we do is we take something called, it looks like a period, a dot, and we call that the decimal point. It's going to work, see, decimal is 10, and the point is going to separate the whole numbers from the fractional parts. In other words, when you see the decimal point, the digit immediately to the left of the decimal point will be the ones place, which means that the digit immediately to the right of the decimal point will be the 1/10th place. So let's see how this works. Suppose I say to you, write 0.07 as a common fraction. One little thing over here. Obviously, the digit to the left, see, I used the decimal point over here. The digit to the left of the decimal point is in the ones place. What is this digit? It's a 0. Well, why do I put it in there if it's a 0? I don't need it. It's a custom to write a 0 in front of a decimal point to avoid careless mistakes. You see, without the 0 here, you may wonder whether that was meant to be a decimal point or whether somebody put the pen on the board and made a mark that wasn't meant to be there. You see, when you see the 0 here, you say, why would the 0 be here if this wasn't a decimal point? But if it bothers you, you could write the thing like this. On the other hand, be very, very careful. The 0 to the right of the decimal point is very important because you see, the first digit to the right of the decimal point is the 1/10th place. And that says what? I have none in the 1/10th place, so where is the 7? 7 is in the 100th place. So I read this as what? The adjective is 7. What place is it in? The 10ths, 100ths, so that's 7 hundredths, which is the same as 7 out of 100, 7 per 100, and that in turn is written as a fraction as 7 over 100. And there is a shortcut for doing this. The shortcut is this. Pretend the decimal point isn't here. Without the decimal point, what would you see here? You would see just a 7. So that becomes your numerator. See, that's your adjective. That's your numerator. I have a pen that's not working very well here. Let me see if I can get a better one here. That's working a little better. See, 7 becomes my numerator. Now, what's my denominator? Here's the trick. Always start your denominator with a 1, because remember, your denominator is going to be a power of 10. Then all you do is come back here and count the total number of digits to the right of the decimal point. And in that situation, zeros count. See, 1, 2. So since there are 2 digits to the right of the decimal point, I put 2 zeros in here. And what answer do I get? 7 100ths, the same as I did before. So that's the shortcut. You say, well, what's the advantage of the shortcut? Well, sometimes when you're dealing with really tiny numbers, it comes in very handy. For example, write, here's a good one for you, 0 point, that doesn't mean anything, 0.000000007 as a common fraction. Now, the long way of doing this is to count the denominations. Tenths, hundredths, thousandths, 10,000s, 100,000s, millionths, 10 millions, 100 millions, billions. See, count the same as you would powers of 10, but put the THS at the end of it. So the answer would be what? 7 1/billions. And this gets messy as the places become more and more, but watch what happens over here. How many digits are there to the right of the decimal point? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I annex 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And lo and behold, I have my 7 1/billionths without even counting that hard. And what does this mean in more intuitive terms? 7 1/billionths means you have 7 parts per billion. And do you notice that there's no decimal there? When I say 7 parts per billion, can you realize that this is a very small concentration? For example, compare 7 parts per billion with 7 parts per 100. Can't you see this is a much higher rate than this one? You see, 0.07 and 0.00000007, the 7 is still the adjective, but the noun that 7 modifies, be it 100 or a billion, is determined by the number of digits to the right of the decimal point. Let's go on and see how this is used. Just as we could treat mixed numbers as a second language, we can also treat common decimals as a second language. Watch what I mean by that. Suppose I said to you, how much is 0.03 plus 0.04? Well, what does 0.03 mean? Without the decimal point, you would see a 3. Since there are 2 digits to the right of the decimal point, it's 3/100ths, isn't it? See, tenths, hundredths, 3/100ths. 0.04 is 4/100ths. See the shortcut? The 4, and the denominator is what? Since there are 2 digits to the right of the decimal point, it's a 1 followed by 2 zeros. So now I've written this in terms of common fractions. What's 3/100ths plus 4/100ths? It's 7/100ths. And how do you write 7/100ths as a decimal? To write 7/100ths as a decimal, you want the 7 to be the digit furthest to the right, but you want it to be in the hundredths place. This is tenths, hundredths. In other words, working in reverse, you say, okay, I want this to be hundredths, therefore this is going to be tenths, therefore the decimal point is going to come over here. And I'll show you a shorter way of doing this later on, but the answer becomes 0.07. Well, unlike mixed numbers, which are difficult to visualize intuitively for most people, once you get the answer to a decimal problem using the second language technique, you suddenly discover a neater way of doing the problem. What if I just lined up the decimal points over here and wrote 0.03 plus 0.04? Couldn't I say that 3 plus 4 is 7? 0 plus 0 is 0? You see, as long as the decimal points line up. See, what's the 3 modifying over here? Hundredths. What's the 4 modifying over here? Hundredths. How much is 3/100ths plus 4/100ths? As long as 3 and 4 are adjectives modifying the same noun, 3 plus 4 is going to be 7. You see, notice that 0.03 is read as what? 3/100ths. 0.04 is read as 4/100ths. Now we're right back to our very first lesson. And my third crayon, I think. Just conspiring against me today. We'll just see what happens here. See, 3 plus 4 is 7, and what's the common denomination? Hundredths. Okay? It's neat. See, forget the decimal point. The decimal point just takes the place of the word hundredths, just like when you write 6,000 and you want to get rid of the word thousand, you have to put in 3 zeros. See? And by the way, whole numbers are special cases of decimals. I should point that out to you because it'll come in handy a little bit later. See, this problem says if we wish to, where may we place a decimal point in 27? See, what does a decimal point do? It helps you locate the ones place. Remember, the ones place is immediately to the left of the decimal point. In the number 27, where there is no decimal point, what's understood to be in the ones place? The 7. See, it's 2 10s and 7 1s. So if you put the decimal point after the 7, you see what happens over here? What does the decimal point tell you? It tells you where to find the ones column. So the 7 is in the ones place, the 2 is in the tens place, so this number is read how? 27. Okay? If there's no decimal point in a whole number, put it after the digit furthest to the right. And now with that in mind, I'm going to show you a quick way of how you multiply and divide using powers of 10. So as a preliminary, I would like you to write 2.7 as a common fraction. Now the easiest way to do this is the thing I showed you before. Pretend the decimal point weren't here. If the decimal point wasn't here, you would have 27. 27 of what denomination? The digit furthest to the right is in the tenths place. So you have 27 tenths. If you use my shortcut, you'd say what? The numerator is 27, and since there's one digit to the right of the decimal point, the denominator will be a 1 followed by a 0. By the way, if you have become comfortable with mixed numbers and they're now a second language for you, you're now bilingual, notice that 2.7 is the same as 2 and 7 tenths, 2 and 7 tenths, and as a mixed number, 2 and 7 tenths is what? 10 times 2 is 20, plus 7 is 27, is 27 over 10. Now, here's what I want to show you, how you multiply and divide by tens. And this is what makes the metric system so desirable to many people. And we'll be talking about the metric system later in our course. Not later in today's lecture, later in the course. Got to lay some more groundwork first. Let's suppose I wanted to multiply 2.7 by 10. See, write 2.7 times 10 as a decimal fraction. By the way, in this course, when I say decimal fraction, it's the same as saying decimal. Fraction is a word for a ratio. Whether it's decimal, mixed number, or common fraction, it's still fraction. So we want to take 2.7 times 10. Let's translate this into our natural tongue, which is common fractions. In the previous problem, we saw that 2.7 was 27 over 10. So this problem becomes what? 27 over 10 times 10. The 10 in the denominator cancels the 10 in the numerator. We get 27 over 1, which is 27. And what did we say? When there is no decimal point, we can always assume that the decimal point is after the digit furthest to the right. So 2.7 times 10 is 27. To all intents and purposes, what did we do here? All we seem to have done is move the decimal point from being between the 2 and the 7 to after the 7. And that becomes the mechanical formula. To multiply a decimal by 10, simply move the decimal point one place to the right, because that will move each denomination up by 10. You see that? See, the 2 was immediately to the right, left of the decimal point. That made it 2 ones. When I moved the decimal point over here, the 7 now occupied the 1's place, and the 2 occupied the 10's place. See, the 2 1's became 2 10's. In any event, to multiply a decimal by 10, move the decimal point one place to the right. By the way, when you learn whole numbers, and I've had students say this to me, they say, when you multiply by 10, don't you just tack on a 0? Isn't that true for whole numbers? I want to show you the danger of that reasoning. Here's an actual thing that happened to me one day in class. A student told me that 2.7 times 10 was 2.70. Before I comment on that, do you understand that 2.7 is the same as 2.70? See, this says what? 2 1s and 7 tenths. In terms of money, $2 and 7 dimes. This says $2, 7 dimes, and no pennies. So this and this are the same. But the kid said, but I learned in school that to multiply by 10, all you have to do is tack on a 0, so he tacked on a 0 over here. The point I want you to see is that tacking on the 0 for whole numbers was in effect moving the decimal point. Because remember what we said? If there is no decimal point, it comes immediately to the right of the last digit. How do you multiply by 10? You move the digit one place to the right, the decimal point one place to the right. How can you move the decimal point one place to the right if there are no more digits? Answer, you use 0 as a placeholder. You use 0 as a placeholder. There are gremlins all over here today. And we're just going to keep working on this till we get a pen that's easier for you to read. But if you use your imagination, even if the pen doesn't work, you'll pretend that you'll see the zeros where I put them. Now, here's the thing. Remember we talked about powers of 10 earlier? Let me show you how this works. Suppose I want you to multiply 0.00234 by 1,000. 1,000 is what? It's 10 times 10 times 10. So I'm going to multiply by 10 3 times. So every time I multiply by 10, I'm moving the decimal point one place to the right. If I'm multiplying by 10 3 times, what am I going to do? I'm going to move the decimal point one place to the right 3 times, which, by the way, is equivalent to moving it 3 places to the right once. So the answer is what? 2.34. See, I take the decimal point and I move it 1, 2, 3 places to the right. And you see, remember what we said in the first lecture? 1,000 is 10 to the 3rd power. See, a 1 followed by 3 zeros. So the 3 tells us what? You're multiplying by 10 3 times, so you're going to move the decimal point one place to the right 3 times. Similar thing for dividing by 10. Can you almost guess the answer here? If I move the decimal point one place to the right when I multiply by 10, what do you think I might be doing when I divide by 10? Well, by this time, you know that the nice versus necessary theme makes you a little bit suspicious. It would seem that you should move the decimal point one place to the left, but we've seen other cases where what you thought would be right gave the wrong answer. So let's not guess. Let's find out. I say, how much is 2.7 divided by 10? Don't guess. Convert everything to common fractions. 2.7 is 27 tenths. Now you're dividing by 10. 10 is 10 over 1. How do you divide? You invert and multiply. 27 over 10 times 1 over 10 is 27 over 100. 27 hundredths means what? The 27, the 7 has to be in the hundredths place, so we move the decimal point 2 places to the left. You see, remember, dividing, we move it 2 places to the left, so now we have 0.27. Now compare the problem with the answer. in 2.7 divided by 10 equals 0.27, do you notice that the decimal point has moved one place to the left? So in other words, to divide a decimal by 10, move the decimal point one place to the left. Look, here's an easy example. Suppose something costs $2.70 and 10 people are splitting the cost of it. How much does each person pay? 27 cents. 27 times 10, $2.70. Isn't that neat? Now suppose instead of dividing by 10, you want to divide by 10,000. You say, okay, how much is 234.6 divided by 10,000? 10,000 is 10 to the fourth, isn't it? That means there are 4 factors of 10. Every time you divide by 10, you move the decimal point one place to the left. Since there are 4 factors of 10, how many places to the left are you going to move the decimal point? You're going to move it one place 4 times. That's the same as 4 places. So you count 1, 2, 3. See, we're moving it now, so I'll put a caret mark there. Then you say, oops, I've run out of places. Whenever you run out of places, you put in a 0 as a placeholder. So the answer is 0.0, 2, 3, 4, 6. And if you wish, you can put the 0 in here just as an indicator. And now I want to show you how you can use this result to decide that 7/100ths, if I didn't tell you before, could be written as 0.07. You see, the idea is 7/100ths means 7 per 100. 7 means 7 with a decimal point after it. Per 100 means divided by 100. How do you divide by 100? You move the decimal point 2 places to the left. Since the decimal point was over here, one place to the left puts it here. Oops, I've run out of digits again, so I put in another digit, and lo and behold, there is my 7/100ths. But you know, again, another theme, the more things change, the more they remain the same. The same problems of sloppiness that would bother us in the pre-decimal stage are going to bother us in the decimal era. You still have to remember that when you use the addition tables, you're always talking about like denominations. For example, suppose I say to you, how much is 27.6 plus 1.84? In this horizontal form, there is a danger that you might say, I'll take the first digit here and add it to the first digit here. Why can't I say that 2 plus 1 is 3 here? And the answer is that by virtue of position, the 2 here stands for tens, but the 1 here is in the ones place, isn't it? Why can't I line up this way? Why can't I add the 6 with the 4? Isn't 6 plus 4 10? Sure, as long as 6 and 4 are adjectives modifying the same noun. But the 6 here is what? Tenths. See, it's the first digit to the right of the decimal point. Where's the 4? It's the second digit to the right of the decimal point. Tenths, hundredths. So it's 6/10ths and 4/100ths. You can't add them. So what do? We use a calculator, which you're allowed to do in just a couple of more lessons. But until that time, what we do is we use the vertical form and line up the decimal points. See, I line the decimal points up. So I write the 27.6. Then I put the 1.84 so that the decimals line up. Then I copy in the decimal point. Then I do this problem the same as if it were whole numbers. By the way, to make this easier to read, I don't have to do this. I put the 0 in here. We'll check this thing out later mathematically, but 27.6 is the same as 27.60. In other words, this is $27.06. This is $27.60, 6 dimes and no cents. But we'll check that out. And what I want you to see is why this works. See, how would you read this number? Without the decimal point, it would be 2,760. And this number without the decimal point would be 184. But since there are 2 digits to the right of the decimal point, we would read this as what? 2,760 hundredths plus 184 hundredths. Since these are like denominations, can't I just add them? See, that's where my 2,944 comes in. But what's the noun? It's 2,944 hundredths. And hundredths means per 100. Per 100 means divided by 100. And when you divide a decimal by 100, you move the decimal point 2 places to the left, and there's your 29.44. But you see the interesting thing here? If you understand whole number arithmetic, once you learn the meaning of the decimal point, you add decimals exactly the same way as you would add whole numbers, because as adjectives, the numbers still mean the same thing. Subtraction is slightly tricky in the sense that when I say to you, how much is 27.6 minus 1.84, that looks very much the same as the problem that we just did. But now, this is very tricky. Most people tend to say, who needs the 0, and they copy down a 4 here. Notice that a 0 is understood to be here. And so if you want to do this problem correctly, you're really subtracting what? 2,760 hundredths. From 2,760 hundredths, you're taking away 184 hundredths. You see, that 0 is really important here. And by the way, how do you check this? The check for subtraction is the same as it always has been. The number you're subtracting added to the difference should give you the number you started with. See, 0, carry the 1. See what I'm doing here? 7, 8 are 15, carry the 1. 5 and 1 is 6, and 1 is 7. 27.60, which is the same as 27.6. See, be careful. By putting the 0 here, the 2, the 7, and the 6 as adjectives never change position. They're still in the same place. However, if I put the 0 between the decimal point and the 6, do you see a dramatic difference? You see the 6 is still 6, but now the 0 is holding the tenths place, so this 6 now names what? 6 hundredths, whereas here it named 6 tenths. In terms of money, you certainly don't want to confuse $27.60 with $27.06, okay? Let's just do one problem that way, just to show that we don't have to rely on money to do this. Let's just work it out by our second language technique. I say our 3.4 and 3.04 equal. They obviously aren't because the 0 here pushed the 4 into a new place. Let's just do this as a second language. 3.4 is 34 over 10. See, 34 tenths. That reduces, dividing numerator and denominator by 2, that reduces to 17 over 5. 17 over 5 can now be written as the mixed number 3 2/5. You see how each module feeds off the previous ones? Almost like life itself. Each generation learns from the previous generations, leaves a heritage for the future generations. Each module will learn from the past and leave a heritage for the future. So 3.4 is the same as 3 2/5. 3.04, see, without the decimal point, you see 304. 2 digits to the right of the decimal point, so it's 304 hundredths. 4 goes into both the numerator and the denominator here. That's the same as 76 over 25. 25 goes into 76 3 times the remainder of 1. So the answer is 3 1/25, which is similar, but certainly not the same answer. It does make a difference. And again, if you don't like to go through it this way, you can say what? 3.4 means 3 4 tenths. As a mixed number, 3 4 tenths can be converted into what? 10 times 3 is 30, plus 4 is 34 over 10. Enough for that, okay? Let's now do a multiplication problem. See, what I'm going to do in today's module is the first 3 of the 4 basic operations using decimals. I've already done addition and subtraction. I'm now going to do multiplication. And because division is nasty because of that stuff about denominators having to have only 2s and 5s as prime factors, I'm saving that for Module 8. So in a certain sense, Module 7 and 8 could be viewed as one long module. Somehow, I just tend to like to always treat division differently from the other 3 operations, for 2 reasons. First of all, division is usually more important because it's related to rates. And secondly, for some reason or other, which we can't go into here, not because we can't go into it, it's just not worth it. It is a rather advanced topic, but from a mechanical point of view, division is usually the hardest to perform mechanically of the 4 basic operations, so I'd like to give you more time to practice that. So let's just finish off today's lecture with a little bit on multiplication. Suppose I say to you, how much is 3.14 times 2.7? I'm going to do something a little bit different this time. This time I'm going to show you the mechanical voodoo way, which I was taught and never learned to understand, but I always got it right because I was a good boy and did what I was told to do. If the teacher said you did it, I did it, because if I didn't, I'd get punished, not just in school, but at home. But that's a different issue. We'll talk about that sometime if it ever comes up. But let me just show you the mechanical way I was taught to do this. We were taught to write this as a regular multiplication problem, but to ignore the decimal point. In other words, the decimal point is in here, but you pretend it's not. And you multiply the same as if the decimal point wasn't in here. Just the same as if this was 314 times 27. And you multiply this out the regular way. See, 8 carry the 2, 9. 21, 8, 2, 6. You add this up, you get 8,478. See if this sounds familiar to you. Then you were told to go back to the problem and count the number of digits to the right of the decimal points. See, 1, 2, 3. See, 2 here and 1 here. That gives me 3 altogether. Then you took this decimal point, and because there were 3 digits to the right of the decimal point, you moved this one always got me. Since there were 3 to the right, you took this one and you did what? Moved the 3 to the left. Do you remember doing something like that? I must be doing something wrong. Even my good pen is deserting me now. So imagine the decimal point between the 8 and the 4 here. So the answer to this problem would be called 8.478. Does that look at all familiar to you? And by the way, if you have trouble with this, I used to figure, what the heck? If there are 3 decimal digits to the right, why don't I move the decimal point from here to the right? I didn't know what I was doing. I just followed instructions. Let me show you how the reward for all the stuff we've learned before still is with us. Look, whatever 3.14 is, isn't it more than 3 and less than 4? Whatever 2.7 is, isn't it more than 2 but less than 3? Again, think of this in terms of money if it bothers you. $3.14 is more than $3 but less than $4. $2.70 is more than $2 but less than $3. 3 times 2 is 6. I don't have to know decimals for that. 4 times 3 is 12. I don't have to know decimals for that either. Now, without even looking at this problem, what have I done? I've bounded it. I know that the right answer has to be what? More than 6, but less than 12. Guys said, well, how does that help you? Well, the way it helps me is, if I didn't know where to put the decimal point over here, where is the only point, the only place I can put a decimal point over here that will give me a number that's between 6 and 12? I can't put it between the 4 and the 7 because 84 is more than 12. I can't put it before the 8 because 8/10 is less than 6. I have to put the decimal point over here. But that's just excitement. Let me show you now how you don't have to rely on anything. In fact, you know, while I was down here, maybe I should show you one more thing. Why not round off the 3.14 to 3, the 2.7 to 3? So 3.14 times 2.7, if I round everything off to the nearest whole number, that comes out to be 9. And now I have a new answer that says what? The right answer to this problem is between 6 and 12, but closer to 9. Okay? But what I wanted to show you before is, let's use our second language technique to solve this problem. 3.14 is what? Without the decimal point, that's 314. Of what denomination? Hundredths. You notice what's happening? I'm going to get a 0 in the denominator for each digit to the right of the decimal point. That's where this counting decimal points comes from. Let me just show you something here. What about the 2.7? Without the decimal point, it's 27. But what denomination? Tenths. So translating this into a common fraction, the problem becomes 314 over 100 times 27 over 10. Now, how do you multiply two common fractions? You multiply the numerators and you multiply the denominators. Well, look, what are the numerators here? 314 and 27. That was why you multiplied. That was why you multiplied as if the decimal points went in here. That's where your 8,478 came from. But you also have to do what? Multiply the denominators. 100 times 10 is 1,000. How do you do that? 1 times 1 is 1. Count the number of zeros. You see where these zeros are coming from? 1 0 from each digit that was to the right of a decimal point. Now, how do you divide by 1,000 using decimals? You move the decimal point 3 places to the left. And that's where your 8.478 comes from. So you can actually verify why these recipes you were taught before work. And see, it still works the same way. Suppose somebody says to me, how much is 0.00314 times 0.27? Without the decimal points, isn't it true that I'm still multiplying 314 by 27? That's still going to be 8,478. How many digits are there to the right of the decimal point? 1, 2, 3, 4, 5 here, and 2 more over here. That's 7 altogether. So what do? I move the decimal point 7 places to the left. But I only have 4 digits, so I have to annex 3 zeros, take this decimal point out. That's 0.0008478. And if you want to see why that works, you see this number is what? 314 over a 1 followed by 1, 2, 3, 4, 5 zeros. This number is 27 over a 1 followed by 2 zeros, 1, 2, 3, 4, 5, 6, 7. I'm going to divide by 10 7 times, and that means move the decimal point 7 places to the left. And now, as far as percents are concerned, they work the same way whether you're using common fractions, mixed numbers, or decimals. Let me just conclude today's lesson with a little bit of percents. Suppose I say to you, write 0.7% as a common fraction. Percent still means per 100. So 0.7% still means 0.7 per 100. I can still multiply both numbers in a rate by the same non-zero number. I want to move this to be a whole number. I move the decimal point 1 place to the right by multiplying by 10. This becomes 7. So at a rate of 0.7 per 100, that's the same as saying you're taking 7 per 1,000. That's 7 over 1,000. And by the way, see, in other words, 0.7% is less than 1%. And how much less is it? You're not taking 1 out of 100. You're taking 7 out of every 1,000. Now, what if I wanted to do this using decimals? See, percent still means per 100. Per 100 still means divide by 100. How do you divide by 100 using decimals? You just move the decimal point 2 places to the left. So that means I have to put in 2 more zeros here. How do I then read this number? It's 7 tenths, hundredths, thousandths, 7 thousandths. That's the same answer I had over here. And once I've done this, I can find a small percent of any number the same way as we did in the previous modules. Suppose, for example, the problem said, how much is 0.7% of 200,000? Well, 0.7% as a common fraction is still 7 parts per 1,000. If I take 7 parts per 1,000 and multiply that by 200,000, do you see the 3 zeros are going to cancel here? And 7 times 200 is 1,400. And by the way, let me just point out one more thing here. If you're counting by thousands, 200,000 is going to be the 200th one you come to. And if you take 200 times, that's 1,400. And by the way, if you wanted to do this as a decimal, this is still what? Forget the decimal point. Just multiply the 7 by the 200,000. That would give you 14 followed by 5 zeros. Now there are 3 digits to the right of the decimal point here, none here. So move the decimal point 3 more places. There's your still 1,400. And another quick way of estimating this is what would 1% of 200,000 be? To find 1%, you chop off 2 zeros. 1% of 200,000 is 2,000, so 7/10 of 1% should be a little bit less than 2,000. Now, I've talked kind of fast. I've done quite a bit, 20 examples today, but the point I wanted to show you is that once you learn this new concept, all the rest that you're doing is an extension of place value arithmetic. All you have to do now is a little bit of practice. Practice, practice, practice. And that's what I'd like you to do before I see you next time. Study hard, have fun, stay young. I'll look forward to seeing you again as soon as possible.